Good day, everyone. This is the demo video for the Group 9 Intelligent Segmentation of Prostate Cancer. This is presented by project team, the two member Zhang Yu and Anandan Natarajan. Just to give the problem statement, currently the pathologist get the tissue sample and go through the manual diagnostic process on segmenting to find what cell is, whether cancerous cell or non-cancerous cell. Go through the Gleason pattern scale of grading between 1 to 5, 1 being no cancer and 5 being the severe cancer. The early we decide and find this problem will be better for the patient to go through the challenges and go through the remediation process. So the current methodology has some drawbacks. It's a time consuming, manual, error prone, and it is not reproducible in a large scale given the dependency on the pathologist. So it might imply on delayed treatment or wrong medication. But with this solution, a high quality segmentation and early detection and diagnosis of prostate cancer is what is the project for this practice exam. So to get into the further, how we thought through that implementation has three stages. The first microscopic biopsy image being going through the pre-processing, image enhancement and image augmentation. Then it will go through the specific model and a different approach on the segmentation. Our data set is a public data set of 888 images of 3100 by 3100 pixel size. So we process it and make it as a 250 by 256 by 256, and we run through various models. Before we get into that, I will let my project teammate Zhang go through the approaches and the demo. Please, Zhang.
Hi, yes. So we try different models. One is deep lab V3 and the UNET due to the computation power, low computation power. So we have choose the UNET with MobileNet V2. Then based on this model, we try two loss function, classic dice coefficient, a multi-dimensional dice coefficient. And we tried various data augmentation methods like rotation, color jitter, Gaussian noise, Gaussian blur, HSV transformation, HED transformation. So after so many methods, we apply the HSV and HED augmentation on our final model training, and we also apply apply the patch pre-processing. And one more pre-processing method we tried is called Outstrew, which can help remove the artifacts or imperfection in H&E stain image. So here is 8 approaches we have tried. So the first one is UNET with the classic dice coefficient, so we can reach 78 accuracy. The second one is a patch processing, like we can reach 82%. So we slide the each original image into 200 times 200 pixels. So the training data set increased to 73K from 100. So then we can see like 5% accuracy increased. Then the third one is we increased the EPO, but it didn't help too much. Then the rest are color space augmentation. Yeah, it helped increase the accuracy about 5% as well. Without the dataset size is not very big, like 1,000 plus. Like we can reach the same accuracy as the patch processing one. So the rest 3 is about we apply different dice coefficient, which is so-called multi-dimensional dice coefficient. So the result is not so stable. And let's do the demo. Let me share the screen. Yeah, so we create a simple UI with Flask. Then the underlying is a RESTful API. So after we upload image, it will send the image to the backend for model prediction. So we have two options. One is RGB with multi-dimensional dice coefficient. Another one is a grayscale with classic dice coefficient. So let's start the demo. So just select an image, click submit. Yeah, we can see this segmentation result. Then we switch to RGB. Yeah, that's yeah. So we can do further work on this one. So one is due to the imperfection in this H and E state image, we can do some thresholding to mask off such artifacts. Another one is since based on this segmentation results, we can do further classification tasks like the cancer grading based on that Gleason grading system. Yeah, the third one is we can currently we are testing on the public data set, so we can apply the same model on the private data set in future. Yeah, that's all from my side.